So section 3.2 is going to be talking about something called the empirical rule and a z-score. So what we're going to be doing in this section is we are going to be using the arithmetic average, aka the mean, and the standard deviation to talk about how much of our data should fall away from the average. Now, before we get started, we can only use this empirical rule if our data is symmetric and unimodal, aka it has to be normal. So, if our data is normal and has an average and standard deviation, what we can say is that most of our data is going to fall around the average. Now, some of our data is going to be a little bit more than average, so plus or minus 1 standard deviation, or a little bit below average. Okay, now if we extend out that little interval even more, so let's say 2 standard deviations, what's going to happen is that we're going to capture even more of our data. And what the empirical rule says is that we're going to capture 95% of our data. So 68% of our data is going to be within 1 standard deviation, 95 is going to be within 2 standard deviations, and then almost all of our observations are going to be within 3 standard deviations, aka that's about 99%. So before we move on to looking at some examples, let's look at one up here. So let's say that an average, okay, so let's say the average person is 68 inches tall with a standard deviation of 4 inches. Okay? So what the empirical rule says is that 68% of people are going to be 68 inches tall, give or take 4 inches. Which means that 68% of people are going to be between 64 inches tall to 72 inches tall. That doesn't mean everyone's going to be there. It says about 68% of people are going to be. Now, 95% of people are going to be 68 inches plus or minus 2 of those standard deviations. Which means that 95% of people are going to be between 60 inches, so 68 minus 2 times 4, and then 68 plus 8, so 76 inches tall. So if we put this up here, what that means is that most people are going to fall around 68 inches tall. We're also going to have 68% of people fall between 64 and 60. Or, I'm sorry, 64 would be over here. This one would be 72. There we go. And even more people will fall between 60 and 72. Now, a key rule is that if you're not in the 95%, so if you're in the bottom 2.5% or the top other 2.5%, we don't call you an outlier, but we do say that you are unusual. All right, so let's look at an example. Let's say that we don't have the detailed data for the heights of people in a classroom, but we do know that the average height was 5.48 feet and our standard deviation was 0.41. And we had 68 students in this class. So what range can we expect 68% of our students to fall within, and how many students would that be in our classroom? So the empirical rule says that if I want to look at where 68% of the individuals will fall, I need to take the average plus or minus a standard deviation. So in this case, that would be 5.48 plus or minus 0.41. which would give me an interval from 5.07 all the way up to 5.89. Now, 68% of 34 students, that would be 0.068, times 34, which we are going to go ahead and round that out. So 0.68 times 34, that should be about 23 students. So I should expect to see 23 of my 34 students fall somewhere in between these two heights. Now, if I want to do 95%, I'm going to have to add and subtract 2 standard deviations now. So that's going to be x bar plus or minus 2 standard deviations. So that would be 5.48 plus or minus 2 times 0.41. Okay, and what that is going to give me is that's going to give me between 4.66 up to 6.3. And to figure out how many students that would be, I need to take 95% of 34, which would give me about 32 students. Okay, so that's my expectation using the empirical rule. Now below I have the actual histogram and the actual height of these students recorded. So if we look at this, let's go ahead and write down the intervals. So 5.07, that would not include the person that's 4.5 feet tall or the 3 people that are 5 feet tall, but it would include this person here all the way up until 5.89, so up until this person. Okay, as well, if I look at the 95% interval, that also would include the person that's 4.5 feet tall, but it would include everybody up until, let's see, we're going to 6.3, so all the way up until here. This person at 6.33 barely wouldn't make it. So let's compare this with what the empirical rule said. So the empirical prediction said that we should have 23 students on one standard deviation interval, 32 on the next, and almost all for 3 standard deviations would be 34. So let's see, our intervals one more time were 5.07 to 5.89. And then 4.66 to 6.3. So let's count how many people were actually on those intervals and compare it to our prediction. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and we actually have 22 students on that interval. Now within 2 standard deviations, we predicted we would have 32, and if we look here, we have 32. As well, if we look within 3 standard deviations now, we see that we actually did capture all of our students. So the empirical rule does a really good job of what we should see when we add and subtract a standard deviation and how much of our data we should capture. So for the next example, the average temperature in Oklahoma is 77 degrees. So x bar equals 77. And the standard deviation is 11 degrees. So SD equals 11. What we want to know is it unusual to have a 53-degree day? So let's go ahead and draw a normal curve and see where 53 would end up. So right in the center, most days are going to be 77 degrees. And if we add and subtract a standard deviation, that's going to capture 68 of our days, or 68% of our days. Now, if we go one more standard deviation out, that's going to be 95% of our days. Now, that 53-degree day would actually be down here, so it would fall in that weird 2.5%. So it would be unusual. And the reason it would be unusual is because it's more then 2 standard deviations from the average. Okay. Now, what this leads us to is it leads us to something called a z-score. So, what a z-score does is it gives us a unit of measuring a relative value. So, what a standard deviation does is that it's a unit that's going to measure how many standard deviations away an observation is from the mean. Now, the reason we use this is because we have a lot of units of measurement. We have feet, we have inches, we have ounces, we have meters, we have money. So what we want to do is that we want to take all of that and put it into a standard unit where we can talk about whether it's typical, unusual, things like that. So here's how you calculate the z-score. Is you're going to take the value minus the mean and then divide by the standard deviation. Now, when you're doing this on a calculator, it's important that you put parentheses around that top part. That way you're telling your calculator that you're grouping those things together. So let's look at an example of where using the standard deviation is very helpful for us. So let's say that we want to look at our exam scores of our friend Nikis. And on the first exam, they get a 73 out of 100, and on the next exam, they get 80 out of 100. So our initial instinct is that they did better on the second exam. However, on the first exam, the average score was a 75 with a standard deviation of 10. And on the second exam, the average was an 83 with a standard deviation of 8. So what we want to know is which exam did they perform better on when we compare them to the class. So to do this, let's look at the first exam, the second exam, and calculate their z-score. So for exam 1, they got a 73, but the average was a 75. So they performed a little bit below average. Divided by, and the standard deviation was 10. On the second exam, they scored an 80, but the average was an 83 with a standard deviation of 8. So for their first exam, their z-score, which should be negative because it's below average, is negative 0.2. And on exam 2, it was negative 0.375. So if we put these on the same normal distribution, the first exam is going to be about here, while the second one will be about here. So they actually scored better on the first exam than on the second one. Ready? Alright, so for the next example, let's look at the average lifespan of a houseplant, which is 36 months with a standard deviation of 3 months. So, if we draw the normal curve using this information, most of our houseplants are going to live 36 months. If we add a standard deviation to 39 and subtract 1 down to 33, that's about how long 68% of our houseplants will live. And if we go one more out, that will be 95%. Okay, great. So the next thing we want to do is find the z-score for two houseplants, one that lived 32 months and another that lived 41. So the z-score is going to be 32, our observation, minus 36, our average, divided by 3, which is our standard deviation. So the z-score for the first houseplant, so let's see, 32 minus 36, that's going to give us a negative 4, divided by 3, which is going to give us a z-score of negative 1.3 repeating. For the second houseplant, which is going to be 41, is going to be 41 minus 36 divided by 3. Now this should be a positive z-score because 41 is bigger than the average. So let's see, 41 minus 36, that's going to be 5 over 3, which is going to give us a z-score of positive 1.6. Now, if we draw these on that normal distribution, let's see, 32 months, so that would be about right here. So that is a little bit less than 1 standard deviation away, whereas 1.6, which would be 41 months, would be about right here, which is a little bit more than 1 standard deviation away. So drawing this normal curve helps us to determine if our answer is correct. Now, for the very last part of this example, let's say that we have a houseplant that has a z-score of negative 1.3, okay? And what we want to do is we want to work backwards. So first, is this houseplant unusual or typical? Well, since it's within 2 standard deviations, it's typical. And is it going to be higher than the average or lower? Well, because it's negative, that means it's going to be lower. Now, what we're going to do is that we're going to work backwards to find how long this houseplant lived. So, remember, the equation is z equals x minus x bar over s. So the z-score is negative 1.3 equals, well, we don't know what x is, that's what we're trying to find, so we're going to have x minus the average. Well, the average hasn't changed, it's still 36. So minus 36 divided by the standard deviation, which is still 3. Now, to solve this, you have to get rid of that denominator first, so we're going to multiply both sides by 3. That means that the denominator and that 3 is going to cancel out, and that is going to become negative 3.9 equals x minus 36. Now, we're going to add 36 to both sides. And what we're going to get when we do that is we are going to get roughly 32.1. Which we could have expected since that's this part of the problem. Alright, great. If you would like to see more examples of this, there's going to be an example video following up shortly. It'll be in the Chapter 3 example video section.